Now this problem isn't exactly like the one we did in class. In fact, it's a little more difficult. We've got a cable and we're laying it across a river from R to T. So can you visualize the river right here? Okay, we've got the river going on. And the cost of laying the cable on land is $10,000 per kilometer, but the cost of laying cable underwater is $16,500 per kilometer. It's more expensive. It's harder to do. We have to decide which point P such that the cost of laying the cable is minimized. So you can see this is a max-min problem. So we need to find the derivative and find the minimum value. So now you'll notice that in this example, I let X be the segment from SP. Knowing that the total length is 4, then 4 minus X would be PT. Now PT is the distance of the cable on ground. Okay, so that's real important. Now, how did I find the distance going under the water? Well, just use the good old Pythagorean theorem. The length of the hypotenuse is the square root of x squared plus 1.2 squared. So now that we've established the variables, let's go ahead and solve the problem. So on your template, you can see I filled in a few things. If you need to pause the video, that's great. So first of all, the question is, at what point should I lay the cable? And I want to minimize cost. So we have to label the defined information. We are told the length is 4 kilometers for the whole distance on land, and then we're told 1.2 is from SR, and we're told the cost for land versus water. And here we have our label diagram. Now, what we are going to be doing is we're going to be laying cable along the river here and then along land. So it's going to be the total distance of the square root of 1.2 squared plus x squared, and that cost is $16,500. So that's how I get the first piece. And then we're going to add it to the cost of laying it on land, which would be the 4 minus x, and the cost is $10,000. Great, so now we have the function written in one variable. Now we have to take the derivative and find any critical points so we can find the minimum cost. So let me shrink this down so I can get a little more space to write here. So then the derivative of this function. So we have a little chain rule going on here. So we're going to have 16,500, and it's going to be times 1/2. Bring the 1/2 in the front. Quantity in the inside stays the same. So it would be 1.444 plus x squared. But we're subtracting 1, so now it's the negative 1/2. And don't forget the chain rule, so it's times 2x, which is in the inside. Now we're going to add that, we're going to add that then to 10,000 times the derivative of the inside, which is a negative 1. And this will be our derivative of cost. Now if I clean up this function a little bit, then I should end up with 16,500x all over the square root of 1.44 plus x squared minus 10,000 is equal to the derivative of the cost. Now, to find the critical numbers, we know that we set the derivative equal to 0 and the derivative undefined. Well, as far as the derivative undefined goes, if you look at the denominator, that denominator will never be 0. So I don't really have to worry about making a common denominator. So let's just worry then about setting the derivative equal to 0. So I'd end up with 16,500 all over the square root of 1.44 plus x squared minus 10,000 is equal to 0. So now let's go about solving this. Now actually, you know what, just to save time, I'm not going to show all the steps. I think you can do the algebra here. And if I were to do the algebra, I end up with x equals 0.914. So that's 0.914. Now if you remember, the 0.914 represents the segment from SP. So if I were to find the amount of cable that would be laid on land, it would be 4 minus x. So 4 minus x then, 4 minus 0.914 is 3.086. So this would be the amount of cable laid on land. And then if I were to substitute x into the hypotenuse, I would end up with, so it's the square root of 1.2 squared plus x squared, I would end up with 1.508 as far as the amount of cable laid underwater. Now, I could, to approximate my cost then, I could say that it's 1.5 for underwater, which is 16,500. And then we have approximately 3 kilometers on land, which is 10,000 per kilometer. And doing the algebra, I end up paying $54,750 would be the minimum cost to lay this cable for this job. Now let's look at the second problem that you did in class. And in class you had a 20 by 30 and you cut out a length x from both sides. So our width now is 20 minus 2x. Our length would be 30 minus 2x because I'm cutting out a side x from each side. And the height would be x. So using the graphic organizer, the question is, what are the dimensions of the box? The width is 20, length is 30, and we know volume is width times length times height. So using the dimensions that we just talked about earlier, we have volume equals 2 times 20 minus 2x, and then multiplied times 30 minus 2x. Now, in doing my algebra and multiplying this all out, I end up with volume equal to, we have 4x cubed, whoops, where did my pen go there? 4x cubed minus 100x squared, and then plus 600x. So this is the function then that represents volume. So in order to find a maximum or a minimum, we must take the derivative. So the derivative of volume would be 12x squared minus 200x plus 600. Now we see that this is a quadratic equation, so there's possibly going to be two solutions when the derivative is equal to 0. Well, when I worked on this problem, I was sorely disappointed because it turns out that I could not factor. Now I took out the GCF, which was 4, and I ended up with 3x squared minus 50x plus 150, but unfortunately it did not factor. So what I did is I graphed the function and found the zeros, and it turned out that I had two zeros. I had one at 3.924, and then I had another zero at 12.754. Well, I could not consider this value because think about it. If I cut out 12 from one side and 12 from the other side, I'm actually cutting out a length of 24, which is greater than the whole width, so it's beyond the domain. So then to get the maximum volume for this cube then, I would approximately need to cut out 4, and was that centimeters, you guys, or just 4 units? 4 units as my length x. And then basically what would happen, it'd be 20 minus 2 x's, so 2 times 4, would give me a width of 12, and then 30 minus 2 times 4 would then give me a length of 22. And then if I multiply that by 4, the maximum volume would be 1,056 units. Now, to the last problem. Now our last problem was talking about the loneliest number. And in this problem, you're trying to find two numbers that have a maximum as large as possible a sum and as small as possible of a sum. So in setting this problem up, the given information is that together the two numbers need to equal 1, and I want to find a sum of their squares that's both maximized and minimized. So let's say we let x be the first number. So if x is the first, then 1 minus x must be the second, because together they do make 1. And I now write my function. X squared plus a quantity 1 minus x squared is the function. So now when I expand that, I end up with 2x squared minus 2x, sorry, my x got blurred up there, plus is equal. So here is the first question. So I ask you to pause the video, do the math, and then put your answer. Now here's the solution to that problem. Remember, you have to take the derivative to find a minimum value and consider the two possible critical points, 0 is not a critical point, so the only critical point is 3, and we can see that it's a maximum. So your value for k is 34. Now here is your second problem. This is an optimization problem, but what's nice, I give you the function. So first, would you answer problem A? At what time is the proportion of normal oxygen level in the pond the least? Here is the solution to part A. So the normal oxygen level is the least when T equals 1, and that would be at 1 week. And here's the solution for B. Now B, you had to find the second derivative because the question asked for when the level in the pond is increasing. That means the first derivative, and then most rapidly. So we want the maximum of first derivative. So you find the second derivative, set it equal to 0, and see when you have a maximum. And we have a maximum at radical 3 weeks. So there you go.